Hi there. Can someone please confirm that they can hear me?
Yep.
Okay, thank you. So this set of announcements is the same as what I've shown before. One update is that the current level of participation in the SRTEs is at 44%. I remind you it needs to get to 75% in order for us to in order for the extra homework, optional homework that people have done to be counted for up to 0.5% of the course grade. I also remind people whose Penn State user ID starts with the letters AA to AQ to please try to ask a good question today in the chat. Up until now, the class has earned 0.55% extra credit on the total course grade by asking those questions. People have asked where you can find the SRTEs. I'm not exactly sure. If someone knows the answer to that, please do that. And it says there are 4 SRTEs listed for this class. The one that I pay attention to is the one for the instructor. I think you might also be filling out ones for TAs, but I'm not sure. Okay, so today we're going to continue our discussion of quantum mechanics focusing on tunneling. And then we'll talk about angular momentum and how the quantization that's created, if you will, by the Schrodinger equation leads to the quantization of space in some sense. And finally, we'll talk about nuclear physics and, if there's time, star collapse. But first, I'd like you all to give a virtual round of applause to your learning assistants who have helped tremendously during this class by answering your questions in the chat during class, which I would have been unable to do on my own. So I do thank them for all their efforts. So last time we were talking about finite potential wells, which I remind you is a physical system where a particle lives inside of a region where the potential energy is 0, and outside that region, to the left of 0 in this case, and to the right of capital L, the potential is given by U0. And if that potential energy is greater than the total energy of the particle, in this case, the total energy of the particle will be its kinetic energy, then that particle, if it's treated just classically, will always be in between 0 and L and never outside at that region. It'll never be in this orange region to the left of 0, nor in the orange region to the right of L. But quantum mechanically, that's not the case. Quantum mechanically, we solve the Schrodinger equation, we find that there is some finite but small probability that the particle can exist in those orange regions. In the process of solving this Schrodinger equation, we basically made just a notation simplification by writing this complicated quantity 2m over h bar squared times u0 minus e as 1 over eta squared. This quantity eta has the units of length and is called the penetration depth. And we calculated what's the probability relative to being right at the edge for a particle to be 10 penetration depths into the region that is classically forbidden, so into this orange region. And we found that this was very, very small, 2 times 10 to the minus 9, so 2 parts in a billion, is the relative probability that you would find a particle even just 10 penetration depths away from the edge. And each of these penetration depths is usually of the order of sort of nanometers or less in size. So the particle really can't go very far into this classically forbidden region. So now what I'd like to do is take these concepts and apply them to a different shape potential. The classical analog is a ball that has some kinetic energy, 1/2 mv squared, and it's approaching a hill of height y max, so that the total potential energy of the ball if it's at the top and not moving would be mg y max. And you know from mechanics that if we set these two equal to one another, that gives us the condition on the kinetic energy that allows the ball to go over this barrier and end up over here on the other side. So, the ball could be over there somewhere if 1/2 mv squared is slightly larger than mg y max. Another way to draw this is shown over here in this figure. So this is the potential energy versus distance. And what you see is if the energy of the ball is less than u0, where in this case u0 is just mg y max, then the ball will start out over here, it'll roll up the hill, it'll get up this high, and then it'll turn around and come back down again. It won't make it over the barrier. By contrast, if the energy is greater than u0, if the kinetic energy is greater than mg y max, then the ball will be able to go up and over, and it'll be on the other side, traveling off on its merry way. Okay, so what we've done until now with microscopic particles and the Schrodinger wave equation is to look at the case labeled here with letter A of a well, a quantum well. So this is like this hill, this barrier, but inverted. So we had finite potential that the particle was in, and we found that not only were the energy levels quantized, but also there was a finite probability of finding the particle somewhere in this classically forbidden region. So we're going to focus on that fact that there's this penetration depth and the particle can be in this classically forbidden region, and take this potential well and kind of flip it so that it forms a barrier now. And what we have in this case is a particle whose energy is not shown, but it could be something like this. So it's some energy less than the potential energy of the barrier. And so the question is, can this particle get through the barrier? We know it can enter the barrier a little bit based on what we saw with the finite potential well. But the question is, can it get through to the other side where its potential energy will again be zero, just like it was in this region here. But now, once it's got through that barrier, it's a free particle. So the particle has effectively tunneled through this barrier, which is something that a classical particle could never do. It's as though, in this case drawn up here, that ball had a kinetic energy that was less than the mgy max, less than the potential energy at the top of that bump, but somehow it managed to get to the other side. So classically, that can't happen, but quantum mechanically it can. And the probability for it to happen, which is not derived here, but it is derived in the textbook, is a negative exponential, and it's equal to e to the minus 2 times the width of the barrier divided by the penetration depth. So one application of this is something called a scanning tunneling microscope, or STM for short. And the basic idea is illustrated in this figure here on the right. So the idea is you have a probe tip made out of some metal, and it's very, very sharp. And it hovers a fixed but very small distance above a sample. And what you're trying to do is get some idea for the shape of the surface of the sample. In this case, the way it's drawn, it's got this wavy sort of sinusoidal structure. That's not necessarily the way things look in general. And the way this STM functions is electrons that are in the probe tip, say there's one right there now, have some finite probability of jumping across this air gap and being absorbed in the sample. The probability of them doing that is small, but it's finite, and it relies on this concept of tunneling. So we can draw what this looks like. That's shown over here. So this is the probe tip. The electron has some energy, and it's trying to get through this air gap, which basically presents a potential barrier for the electron in order to get over to the sample. So there's some finite probability that this electron will be able to do that. It'll be able to tunnel from the probe tip to the air gap. Of course, that probability is going to be pretty small. And I just want to make sure that you realize there's a contrast here between what's going on in this situation and what happens in the situation where we have the photoelectric effect. In the photoelectric effect, there's a light that is illuminating the material that has electrons in it, and it's basically pushing the electrons out of the material. And then those electrons, you can measure the current that gets produced as those electrons get pushed out of the metal that you're shining light on, and then they travel across from between the anode and the cathode, and you can measure that current. In this case, there's no light being shined on this probe tip or on the sample. Instead, we're relying on the small probability that an electron can basically jump across that gap. It doesn't get pushed by a photon. It just jumps by virtue of quantum mechanical tunneling. And it's not just one electron that does this. Of course, if there's some finite probability, even if it's a small probability for an electron to do that, there are bazillions of electrons in here. So if there's some finite probability and it's tiny, but there are a large number of electrons, then you can get a measurable current flowing across this gap. And it turns out that tunneling probability depends very strongly on this distance here between the probe tip and the sample itself. And that's what allows the STM to make images that are at the scale of atoms. So for example, here are a couple of those images. On the left there is something from a biological sample, and the scale here is sort of like tens of nanometers. So that's unbelievable resolution. And then on the right is an image of a molecule, copper azurin. I'm not sure I'm pronouncing that right. And this shows you how you can gain understanding and insight into reactions, in particular surface reactions, by figuring out what the surface actually looks like on the material that you're studying. So STM is a very powerful tool. And let's quantify how it works as follows. So first, I remind you that the tunneling probability is given by this exponential, and the penetration depth, eta, is given by that expression there. So in order to quantify STM, we're going to first calculate what the probability is that an electron can tunnel through a gap that's 0.5 nanometers, half a nanometer air gap, from a metal to an STM probe. So I was saying that the electron here would go from the probe to the sample, but of course it can also go the other direction. It depends on how you set up your potential difference and so on. Okay. So that's one question. If the work function is 4 electron volts, if that's how much it takes, that's how tightly held those electrons are in the sample. And the second question, B here, is if this probe passes over a feature that's 0.05 nanometers tall, by how much does the measured current change, and by what factor? And finally, if the apparatus that you have, the STM, is sensitive to a 10% current change, so a current change as small as 10%, then what size features is it capable of resolving? So to answer all those questions, we plug in some of the numbers here. And the first thing is calculating this penetration depth. And it's roughly 1/10 of a nanometer for this situation where m is the mass of an electron and so on. And the tunneling probability, therefore, is given by e to the minus 2w. And here w is just the width, which is 0.5 nanometers. And eta is this 0.0972. And we put those things into the exponent, and we get 3.4 times 10 to the minus 5 as the probability. Now that's a pretty small number for a probability, but if you have, Avogadro's number of electrons available, and you multiply those electrons by 10 to the minus 5, you still have quite a few electrons left over, or you still have quite a few electrons that are going to make this tunneling, and you can measure the current that they would produce. Furthermore, if this probe tip goes over a little region that has a bump in it that's 0.05 nanometers high, so this is really tiny we're talking about now, by how much would the current change? And in order to figure that out, we change the distance from 0.50 nanometers to 0.45 nanometers. So we change the distance by just 0.05 nanometers. And if we do that, the probability of tunneling changes from 3.4 to 9.5 times 10 to the minus 5 by nearly a factor of 3. So this is an exquisitely sensitive device to be able to have such a gigantic change in the current for such a tiny change in the distance between the probe tip and the sample. And we can further characterize that by saying, well, if you could measure a 10% difference in current, what distance change would that correspond to between the probe tip and the sample? And if you do that calculation, you see that an STM can resolve distances that are 1/20th of an atomic diameter, which is exceedingly small, obviously. Okay, so I'd like now to move to atomic and nuclear physics. This is going to be a sort of a whirlwind tour. And I'll start out with atomic physics, talk about the hydrogen quantum numbers, L and M. We've already talked about the quantum number N. So N we've already done, and now we're going to do L and M. And this is related to the quantization of angular momentum. And then we'll also talk about the radial wave functions written as capital R as a function of the radius R from the center of the nucleus out to the electron. And then we'll talk briefly about nuclear physics, talking about nuclear structure, size, and density, possibly, if we have time, nuclear stability and binding energy. All right, so we've solved the Schrodinger equation in one dimension, but obviously that's an approximation because atoms, in particular the hydrogen atom, exist in 3 dimensions. So in order to really fully solve the Schrodinger equation for the hydrogen atom, or for any atom, you need to move to 3 dimensions. And the solution there is mathematically complicated. It's doable, and I suspect many of you have the mathematical background to fully understand all the steps involved. If you are interested, I'll put in a plug here for Physics 237. That's the next course in the introductory physics sequence where the Schrodinger equation is solved in 3 dimensions in all of its glory. But here we're just going to briefly touch on the results of doing that, that solution. So we already know from our one-dimensional solution that the energy is quantized, and the quantum number associated with that is the letter n. Since we're solving in 3 dimensions, we expect that there will be 3 quantum numbers popping out. And indeed, the other 2 quantum numbers are lowercase l and lowercase m. Lowercase l is for the total angular momentum, capital L, and lowercase l can vary between 0 and n minus 1. And it gives you the value of the total angular momentum, which is square root of whatever that value of L is times L plus 1 times h bar. And then the solution of the 3-dimensional Schrodinger equation also tells you that the projection of this angular momentum L has particular values, namely integers from minus L up to plus L, labeled m, times h bar. So the 2 things that we now have are that in addition to energy being quantized, we now also see that angular momentum is quantized. So if you plug in different values of L here, you see, for example, if little l is equal to 0, then we just have h bar. If little l is equal to 1, then we have square root of 2 h bar, and so on. So those are the values that L can assume. And furthermore, once you measure that L, its direction is also quantized. Its projection along some arbitrary z-axis, and since the z-axis is arbitrary, that means that no matter how you do this, you're going to find that you get quantization of the direction that L can point. So just to do a little example problem, let's summarize what we have so far. So those are the 3 quantum numbers we now have available to us. For the case where hydrogen is in the n equals 4 state, how many different quantum states, which are labeled by combinations of these 3 numbers, n, l, and m, are available to the electron? Each of these states represents a different orbit that the electron can have. So there are different ways to do this. The way I'm going to do it here is just to basically enumerate all of these possible quantum states. So for example, if we assume, if we start out, I should say, with n equals 4, of course, then L can range between 0 and 4 minus 1, or 3. So if we choose L equals 3, then that means that m can vary between minus 3 and plus 3. So I can have 4, 3, minus 3. I can have 4, 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. So those are all the so-called triplets that you can have. And I haven't written all the numbers in here just to save some time. And you look at the total number, it's 1, 2, 3, 4, 5, 6, 7 of them. And you can keep doing that, but now we can set L equals to 2 instead of 3. And then if you do that, if you do the counting, you'll see that there are 5 possible states. And if you set L equals to 1, you'll see that there are 3 states, and L equals 0, you see there's 1 state. And if you add them all together, you see that there are a total of 16 possible states. 16 possible combinations of n, L, and m. So 16 possible different orbits that the electron can have. I am overlooking a factor of 2 here, which some of you may realize already. So there is an additional quantum number that we're not going to consider here, which is due to the fact that the electron itself can exist in one of 2 quantum states, basically called spin up and spin down. So it has an additional 2 states available. So the total number of states is actually 32. Okay, moving back to the angular momentum, let's do as an example L equals 2. So if L equals 2, then the square root of L times L plus 1 is the square root of 6. So the total angular momentum is the square root of 6 h bar. And that further means, if L equals 2, that the z component can assume one of these 5 values. So this means that once you measure L, it is only allowed to lie on one of these green tinted surfaces over here. So let me explain this diagram. First of all, let me remind you that if you have a particle going around in a circular orbit, then the angular momentum is defined to be perpendicular to the plane of that orbit. And its direction by convention is defined by the right-hand rule. So you curl your fingers around the direction that the particle is orbiting, and then your thumb points in the direction of the angular momentum. So if you focus your attention on this m equals 2 vector shown here, it corresponds to an orbit that's tilted at that angle. And if you run your fingers around the direction of that orbit, then your thumb will point in the direction of L in that case. And what this says, with the fact that L sub z is equal to 2h, what this says is that this angular momentum vector here can only exist somewhere on this cone here, because only on that cone does its projection onto the z-axis give you this 2h bar. That's for the case of m equals 2. If m equals 1, then it can only exist on this cone below there. If m equals 0, then it can only exist in this plane here, which has a projection. This is like the cone, but it's flattened. So it has a projection of 0 onto the z-axis. And in a similar way, you can say for m equals -1 and m equals -2, the angular momentum vector can only reside on the surface of those cones. So what this basically says, in some sense, is that space itself is getting quantized. So once we choose a direction and we measure L, we find that its projection onto the z-axis can only have certain values, and therefore there are only certain regions of space where this angular momentum vector, or where the angular momentum itself can actually point, which seems a little strange. But quantum mechanics generally is filled with strange things like that. Okay. When we solve the Schrodinger equation in 3 dimensions, it's done using spherical coordinates. And as you may know, one of the spherical coordinates is r. The other 2 are theta and phi, the angles theta and phi. And we're going to focus on the radius, r. And the functions that are derived from when you solve the Schrodinger equation in 3 dimensions are basically can be split up into 3 different pieces. A piece that depends on r, and a piece that depends on theta, a piece that depends on phi. We're going to focus on the piece that just depends on r, and we're going to look at these radial wave functions, which are labeled with capital R. So that capital R is the wave function, it's not the radius. The lowercase r is the wave function. And this gives us, if we square it, the probability per unit volume of finding an electron. So if you want to find the probability of finding an electron, you got to multiply by this delta V. Now, if you're thinking radially, if you have a sphere and you have then a slightly larger concentric sphere around it, so 2 spheres here, just one slightly larger than the other, they're both out at roughly the same radius, and they're separated from one another by delta r, a very infinitesimally small distance. There is some volume in between those two spheres, and that volume is what this delta v is. And geometrically, it's given by 4 pi r squared times that delta r, the distance between the two spheres. So if we multiply the square of this radial wave function by that delta v, then we get the probability. And that's what's written up here. So the delta v is written out as 4 pi r squared delta r. Down here are some of the possible radial wave functions. We can focus first on the simplest one, this one. So it shows that there's some normalization out in front. And this normalization is there to make sure that when you integrate from 0 out to infinity for r, that you end up getting a unit probability. And then there's this exponential, which basically says that this electron is going to be less and less likely to be found, farther and farther away. If you look at the probability, which takes the square of this radial wave function and multiplies it by 4 pi r squared delta r, then you get figures that look like this. So let's just focus on this first one here. So this is the probability on the y-axis, and on the x-axis is the radius in units of the Bohr radius, a sub b. And you see that for the thing labeled 1s, so 1s means that n equals 1 and L equals 0. You see that the curve peaks at roughly 1 Bohr radius, which is kind of what we expect, because that's where the ground state electron in hydrogen orbits. It's out at about 1 Bohr radius. And then it sort of decays after that. As you get farther and farther away, eventually it's unlikely to find the electron very far away. Okay. So these radial wave functions that we wrote down, focusing again just on the 1s one, suggests that the electron in hydrogen will often be at the nucleus itself, like right on top of the proton in the case of hydrogen. Because if you look at this equation for R1s, if you put in R equals 0 in that equation, then you're going to get the largest value for R1s. As you increase R, you have e to the minus R over a sub b, that quantity gets smaller and smaller. So these radial wave functions suggest that the maximum probability should be at R equals 0, but these plots showed, kind of the opposite, or at least they show that the probability at R equals 0 is basically 0, and it peaks at the Bohr radius. So why is this the case? So I'm giving you a poll where you can answer this question. Okay, get your answers in, please. Okay, so most people chose C, which is the correct answer. As you move closer and closer, as the radius gets smaller and smaller, if you look at this probability function here, we have a 4 pi r squared multiplied by the square of this radial wave function. So we have a 4 pi r squared, or basically an r squared, times an e to the minus 2r. And so this is going to go as r squared e to the minus 2r, this probability. And you can see that as r gets smaller and smaller, the dominant term is going to be this r squared. So it's going to drive the probability to 0. And then as we get to larger and larger r squareds, this exponent is going to be the dominant term, and it's going to drive the probability down to smaller and smaller values. Okay, good. So now I'd like to switch gears slightly and talk about nuclear physics. First, some definitions. So a nucleon is either a proton or a neutron in the nucleus. And Z is the number of protons that are in the nucleus. This is also known as the atomic number. And capital N is the number of neutrons. The sum of those two, Z plus N, is abbreviated with the letter A, and that's the total number of nucleons in the nucleus. This is also called the mass number. An isotope is an element that's the same but has a different A because it has a different number of neutrons. Something we haven't covered in this class is something called the Fermi exclusion principle, which originally was applied to electrons. It basically says that no two electrons can have the same exact quantum numbers, so they can't exist in exactly the same state in the atom. And the same is actually true for nucleons in the nucleus. They also obey the Pauli exclusion principle. The mass of the neutron is greater than the mass of the proton. And what's shown over here is a table of these masses. The fundamental unit that is used typically is the atomic unit U, which is 1.66 10 to the minus 27 kilograms. And you can see that the electron is exceedingly light on this scale. The proton and the neutron are pretty close together in mass, but of course the neutron is heavier. And we also see the masses for some elements, hydrogen and deuterium, which is hydrogen, but with a proton and a neutron in the nucleus, and then an electron around it. Let's focus on deuterium, actually. So again, it's a proton and a neutron in the nucleus, and then an electron around it. And let's compare the mass of deuterium, which is given by this expression here, this number here, with the mass of the individual particles, nucleons and electron, that make up deuterium. So if you do that comparison, what you see is that, well, the mass of deuterium from that table is 2.01410. And if I sum up the masses of the constituent particles, I don't get the same number. So why is this? What causes this? So I'm going to give you this poll so you can answer the question. Okay, please get your answers in. All right, most people answered B. That's the correct answer. There is binding energy that's holding together the proton and the neutron in the deuterium nucleus, and it takes energy to separate them. So When they're bound into deuterium, they have less mass than when they're free. Now the electron is also bound, of course, and that contributes to the mass difference, but it's really, really small on the scale of things, because the force that's holding together the nucleons is much stronger than the force, the electrostatic force, that holds the electron in orbit around the nucleus. And in fact, it's so much stronger that physicists who are so clever with language decided to call it the strong force. That's what holds the nucleons together inside the nucleus. And it takes energy to separate a nucleus into its constituent protons and neutrons, just like it takes energy to remove electrons from a neutral atom, to ionize a neutral atom. The energy that it takes to pull apart all of the nucleons in a nucleus is called the binding energy, and it can be written either as the sum of the masses of all the protons plus all the neutrons minus the mass of the nucleus, or if you want to include the electrons, you get the same result. Here you have the mass of all the hydrogen atoms that make up the nucleus, and that basically means all the protons in the nucleus plus all the electrons that are around the atom, plus all the neutrons minus the total mass of the atom. This figure here summarizes sort of everything we know about the binding energy of nucleons in nuclei. What it shows is the binding energy per nucleon here. So basically says, what's the total binding energy of this nucleus, which has atomic number A? And then you divide that number, the total binding energy, by A, and you get the binding energy per nucleon. It's kind of like the average binding energy per nucleon in the nucleus. And what you see in this figure is that it grows dramatically as you go from lighter to heavier, and then it starts to decrease again as you get heavier and heavier still. The peak here, the maximum, is where iron is located. So the iron nucleus has the highest binding energy per nucleon of any nucleus. So in the chat, I wonder if any of you can tell me which region tells you why fusion works to power stars. And fusion is where lighter elements are put together to form heavier elements. This usually happens in the core of stars, and energy gets released in the process. Also, I wonder if you could tell me which region tells you why fission works to power reactors. So fission is when you take a heavier nucleus and you split it into pieces, and then energy is released. And the regions that I guess maybe you could think of are to the left of the maximum and to the right of the maximum. So for the first question, which region tells you why fusion works to power stars? Is it the region to the left or to the right of the maximum? So yeah, left is for fusion and right is for fission. Very good. So this region over here shows you what happens most of the time when lighter elements are fused together to form heavier elements. You get energy released because the binding energy becomes larger and larger, more and more negative, if you will. And so energy is released as you move in this direction. In a similar way, as you move from heavier elements like uranium-238 down in this direction, you move also towards higher binding energy per nucleon. And so energy is also released if you move from the far right to the left. Now you can see from this figure, one of the reasons why we'd really like to be able to get fusion to work as a controlled energy source. And that's because if you look at this plot, the curve, pardon me, is really sharply, is much steeper, I should say, on the left than it is on the right. So there's much more energy per nucleon available if you fuse lighter nuclei together to make heavier ones than if you fission or split heavier nuclei to become lighter ones. So fission reactors operate going from the far right to the left. Fusion reactors, which don't yet exist, but do work in the core of stars, move from the left to the right, and you get a lot more energy that way per nucleon. So let's estimate the total energy that's released if we fuse 3 helium-4 nuclei, so these are basically alpha particles, to form a carbon-12 nucleus. So what we need to do this calculation is to look at this figure. And if you look at this little blow up here, you can see that helium is just above 7 MeV per nucleon binding energy. It's 7.2 actually. We have 3 helium nuclei that we're fusing together, and each of them has 4 nucleons. So the total amount of energy, binding energy, is 3 times 4 times the average binding energy per nucleon of 7.2 MeV, for a total of 86.4 MeV binding energy. For carbon-12, the binding energy per nucleon is 7.7, which you can also roughly read off of this figure here. And the total binding energy, therefore, is larger, 92.4. The difference between those two is how much energy gets released when 3 helium nuclei fuse to form carbon-12. It's like 6 MeV. This is not the main way, but it's one of the ways that stars power themselves. And by that, what I mean is a star is always fighting off the tendency that gravity has to compress the entire star down into a dot, you know, because gravity just wants to pull everything together. So it's the self-gravity of the star is trying to cause it to compress. What keeps it from doing that is the fusing of elements in the core of the star that produces energy, so high energy photons, that basically push back out against this inexorable gravitational pushing in. So this is a radiation pressure that is produced by the fusing of lighter elements into heavier elements and the subsequent release of energy in the form of photons. This is also, by the way, how most of the carbon that's in your bodies gets produced. So it's made in the core of stars. Okay, I'm going to skip over this next problem in the interest of time. I'll leave it in the slides and just finish up with this final example problem on the fate of stars. So a star like our sun is powered by these fusion interactions. And what's happening is lighter elements are being fused to heavier and heavier elements. But that can't go on forever. So you fuse the elements to carbon and then to oxygen and so on. Eventually, the elements get fused to make iron. And remember from that curve here, iron is right at the peak. So once you reach iron, which has the maximum binding energy per nucleon, you basically have run out of options. So the iron at the core, you can no longer fuse that with some other element in order to make a heavier element and release energy. No energy gets released by doing that. You also can't split iron and fission it in order to get energy to be released. So The formation of iron in the core of a star is basically an energy dead end. There's no way that the star can create more energy at that point in its core. So the radiation pressure that was formerly pushing out on the star and preventing it from collapsing goes away, or it gets dramatically reduced, because the iron that's at the core can't release any energy by fusing or fissioning. And consequently, what happens is eventually the star realizes that nothing is pushing it out and it collapses. So all this stuff outside, from hydrogen and helium, oxygen, carbon, whatever, collapses down onto this solid iron core. And when that happens, of course, it builds up a tremendous amount of energy as it rushes in towards this iron core. Then it hits the iron core and bounces back out again. And that's a supernova. So that collision releases a huge amount of energy, and basically all of these particles and a lot of heat gets released in a very short amount of time. What can also happen in those instances is if there's enough mass of the star, then when it falls onto the iron core, it can have enough mass to crush all of the protons and electrons together and cause the iron to not be elemental iron, but instead to make everything into basically one gigantic nucleus. And this is called a neutron star, which is a macroscopic object made up entirely of neutrons with nuclear densities. So let me just answer this one question here, and then we'll finish up. So the question is, how much would 1 cubic millimeter, a millimeter is pretty tiny, okay, 1 cubic millimeter of neutron star material weigh on Earth? And we're going to give our answer in terms of fully loaded Boeing 747s. And the answer is pretty incredible. 700 fully loaded gigantic aircraft weigh as much as a cubic millimeter of neutron star material. So this tells you two things. First of all, neutron star material and nuclei in general are very, very dense. Conversely, it tells you that most of the matter around us, you know, the wood of my desk, for example, which seems really solid to you and to me, is actually mostly empty space. Okay, I'll finish with that. On Thursday, I'm going to be doing some questions and answers based on questions that have been posed by you in the mini surveys. And that'll be the last day of class. So I'll see you on Thursday. If there are any questions, I'll stick around for a little while longer. Bye-bye.